So when we talk about the rate of a chemical reaction, we're talking about how fast does the reaction make products or use up reactants. So here's some pictures. This is an example of a reaction with a fast rate. So we've got a blue thing and a red thing combining to make a green thing. At the very beginning, it's all red and blue. And we go 15 seconds, 30 seconds, 45 seconds. And we see by 45 seconds, all of the red and blue things have reacted. That's a pretty fast reaction compared to this one, where we've got this kind of olive green and blue reacting to form something pink. Again, we're starting with just reactants, but after 45 seconds, we have some product, but we still have some reactants left because that reaction occurred slower. For it to be complete, we need to wait longer. So the rate of a reaction is in some ways like rate of travel or rate of speed, right? So somebody going down the highway at 55 or at 75, they're going to get where they're going in different amounts of time because of how fast they're going. So the reaction will get to completion in different amounts of time because of different rates of reaction. Anybody have any questions? So rate is how much the quantity changes in a given period of time. If we're talking about cars, we're talking about the distance traveled, probably measured in miles in a given period of time, such as an hour. So we have units of miles per hour. The speed is the change in distance divided by the change in time, or in symbols we could say delta x over delta t. So the rate of a chemical reaction is measured in a similar way, although the reaction is not like moving through space, right? But we're going to look at the change of the amounts of reactants or products divided by the change in time. So we're going to look at this reaction between hydrogen and iodine to form then a nice friendly molecule. It's all caps, so it's kind of loud. Right? The change in the concentration of the reactants is going to be negative because you start with the reactants and then they get smaller and smaller, so that's a negative change. The change of the products is going to be positive because you started with 0 and you're making more. So when we talk about the rate of a reaction, the rate always has to be a positive number. There is one rate for the reaction. We can describe it in terms of different reactants and products. So we could say that the rate is the change in hydrogen, which is going to be a negative number, divided by the change in time. So we're going to put a -1 in there to make the rate positive. We could define it, let's see. So when we talk about delta generally means final minus initial. So this is the hydrogen at time 2 minus the hydrogen at time 1. So if we have less hydrogen than we started with, this number is going to be negative. So for reactants, it's always going to be negative. And then the change in time will be positive, the time elapsed. So what you end up with and what you start with. So if we look at the iodine, we could describe the rate in terms of the change in concentration of iodine. Again, this being a reactant is going to be negative. So the change in concentration divided by the change in time. Any questions? Well, just a word about questions. I know it can be hard to ask questions in a class who's like, everybody else knows what's going on and I'm clueless. The truth is not everybody knows what's going on. Most people are at least slightly confused, okay? So if you ask a question, you're not only helping yourself, you're helping other students. And what's the purpose of being in this class? Is it to show the other people that you're really smart and don't need help with anything? Is that why you're here? No, because you don't know these people. Why do you care what they think of you, right? You're here because you need this class for your major so that you can get into the profession that you want. Don't let the opinions of somebody that you might not ever see again after the semester ends affect your learning, okay? So I really, really encourage you to ask questions. I do my very best, and I don't think I've ever failed at this. I will never try to intimidate you or make fun of you or make you feel bad about asking a question, okay? Because all questions are valid. Okay, so rate. We can also define the rate in looking at the change in the product of the reaction. So the product is high, and this is going to be increasing in concentration. So the rate is naturally positive. The change in that concentration is going to be positive, so we don't need to put a negative sign there to make the rate positive. When we talk about, traveling 55 miles an hour, we don't say, oh, well, I was negative 55 miles an hour because I was going south instead of north, right? It's just always positive. You indicate the direction some other way. So rate of reaction is always positive. Now, when one hydrogen reacts with one iodine, you make two hydrogen iodides. And so this is going to be forming at twice the rate that these are disappearing. And so that's why we need to have this little fraction in here. So this 1/2 is coming from the stoichiometry of the reaction. So this is 2HI, so it's 1 over that number. The HI increases at twice the rate, and so we have to have one rate to describe the reaction. We can describe it in terms of any of the reactants or products, but the rate is the same. So in order to have this rate described in terms of the concentration of HI to be the same number as the other two, we need to multiply by 1/2. So we take this coefficient, and it's 1 over the coefficient. When we looked at these guys, there was no 1 over anything. You could write 1 over 1, but you don't need to. Just like we don't write a coefficient of 1 here, we don't need to put the fraction in. But if there's a coefficient that's not 1, then it's 1 over that coefficient. So reactant concentrations are going to change with time. They're going to decrease. So here we have a graph showing concentration as a function of time. So this is the hydrogen concentration. It started at 1, and as time goes on, it's going to decrease because it's reacting, it's disappearing. This red curve is showing the concentration of the product high. So this is increasing. So the reactant concentrations are decreasing, the product concentrations are increasing. Does that make sense? This product concentration is increasing twice as fast as the hydrogen is decreasing. And that's because of the stoichiometry of the chemical reaction. We could look at the rate of the reaction by looking at the slope of this line. Now this isn't it's not a linear function, it's a curve. So the rate is continually changing, but at any given point in time, we could find the slope by drawing a tangent to the line and looking at the rise over the run. So the change in the concentration divided by the change in time. So at 50 seconds, we've got 0.56 over 40. And here, at 50 seconds, we're looking at negative 0.28 over 40. And so this is changing at a slower rate than that is. So if we take 0.28 and multiply by 2, we get 0.56. So the slope is twice as large because we're making 2 for every 1. Does that make sense? So the average rate decreases as the reaction progresses because the rate depends on the concentration. As the concentration gets smaller, the change is going to get smaller, the rate is going to decrease. So here we have some data. We have at different times, they measured the hydrogen concentration. So if we want to look at the rate, between the first point and the second point, we can find the change in the concentration. That's this one minus that one. And we can find the change in time, 10 minus 0. And we take, we've got the change in hydrogen over the change in time, multiplied by negative 1 to make it a positive number. So we get 0.0181. We can do that for each pair of points. And what we see here is that the rate is getting smaller and smaller. Okay? If we look at this graph, the slope here is steeper than it is down here, right? The slope is equivalent to the rate of the reaction. The slope is getting smaller and smaller. Any question? So the average rate would be the rate over a period of time, like we did in that table. The instantaneous rate, you would look at one point in time. And so this is where we draw the tangent line and we see what's the slope here. Because over here the slope's going to be different, and here the slope's going to be different, right? It's continually changing. So we can find the slope of a tangent line. Now, tangent line's slope compared to of a curve, that just sounds not very useful, right? It isn't very useful. We don't actually look at it that way. But it's a good way to start talking about it because we can see it on the graph and we see what it's representing, right? So the rate is how fast the concentration is changing in a given period of time. So let's look at a generic reaction, A moles of A plus B moles of B, forming C moles of C and D moles of D. Boring, right? These lowercase letters are representing coefficients, and these are the chemical formulas for the reactants and products. So we can say that the rate of this reaction is equal to, we're looking at a reactant here, A, so we're going to put negative 1 over the 1 over the coefficient, times the change in A, which is going to be a negative number, divided by the change in T, the time. We could look at it in terms of B, a different reactant. So find the change in the concentration of B. It's going to be a negative number because it's going down, it's reacting, it's going away. So we put a negative here because the rate has to be positive. The amount that it changes divided by the amount of time that it took, and then 1 over the coefficient, because the stoichiometry affects how fast each of these things is happening, but we have one rate for the overall reaction. For the products, we're going to have these be positive. You don't need to write the positive symbol there, the plus sign. We put it there just to, contrast with this negative. So the change in concentration of product C, it's going to be going up, will be positive, divided by the change in time. And so we'll multiply it by 1 over the coefficient, which is what we did in the previous example. We had 1 over 2, because the coefficient on high was 2. So if we know the rate of change of one of these species, say we knew the rate of change of B, we know delta B over delta T, we can use this relationship and figure out what the rate of change of any of the other things are, products or reactants, because they are all related to each other. So we can see what's happening at that moment in time, but we can't predict what's going to happen in the future, other than the rate's probably going to go down, but that's about all we can say. So we're going to do some examples here. So this is what the slide in your notes looks like, and it's blank there. And I'm going to write on the slide, and I strongly encourage you to write on your paper, follow along, and do the problem. A good thing to do after class is to go back and try to do these problems on your own, right? So if you're using your notes, just cover up what you wrote and try to do it again. If you get stuck, then you can look at what you were writing. If you're really stuck, you can go to the video and find this point in the video and listen to me explaining it. And as soon as you're like, oh, I know what to do next, pause it, and then try to finish it. And you're like, oh, I got stuck again. Well, listen to me explain some more until you can get through it all. And that's how you're really going to learn and understand how to do these things. You can go to a piano concert and see this virtuoso, and they're playing the piano, and they make it look so easy, right? Or maybe a better modern illustration would be, Reels or TikTok videos, right? This guy's playing the piano, and you're like, how does he do that, right? But it looks so easy. It's effortless, right? Well, you can't just go do that after watching him, can you? So you may sit here and watch me solve these problems and say, oh, well, that was easy. Well, it's easy for me. I've been doing it forever, since before you were born, actually. But this is probably brand new to you. And so you're going to need to practice. You're going to need to make mistakes and struggle through it. I would encourage you to go through these right after lecture as soon as you can, because some of this stuff will assume that you know for the next stuff, because we're going to go on and it's just going to build on itself. Okay, so we're looking at this balanced chemical reaction, and it says in the first 10 seconds, the concentration of I- dropped from 1 molar to 0.868 molar, and it's asking us to calculate the average rate of this reaction. So we need the equation for the rate of the reaction. So the rate of the reaction, this is a reactant, right, iodide, so it's going to be a negative. And then we're going to have 1 over the coefficient, 3, 1 divided by 3, times the change in the I- concentration, divided by the change in time. That's what we just learned how to do from the chemical reaction equation. So in words here, they gave us the information we need to find delta I- and delta T. And just in case you don't remember, when we put a chemical formula inside of brackets, we generally mean the concentration in moles per liter of that thing. So this is the change in the concentration. So they tell us that it started at 1 and went to 0.868. So delta I- is the concentration at the second time minus the concentration at the first time. So it ends up at 0.868, and it started at 1. That was kind of messy. I left my calculator at home. That's pretty sad. .868 minus 1. So this is negative 0.132 molar. And we were expecting a negative number because the concentration is going down. The change is negative. What's delta T? 10 seconds. They just flat out told us that part. In 10 seconds, it changed this much. So now we can plug these things into our little equation here. Negative 1 over 3. Delta I- is negative 0.132. Change in time. Well, actually, let's keep the units in there. And this is 10 seconds. So then we've got negative 0.132 times negative 1 divided by 3 and divided by 10. And we get 0.0044 And the units are going to be molarity per second. So, any questions? Yeah. Yeah. Okay, so the book's answer is 4.40 times 10 to the minus 3. So they're just expressing it in scientific notation. So that's part A. And they're saying, determine the rate of change in the concentration of hydrogen ion during this time interval. So let's remember what we had. So we had 0.0044 was the rate of the reaction. So the rate is 0.0044, and I was sloppy with my sig figs. It should have had a 0 there. So that's the rate. What this is asking, though, is what's the rate of change in the H+. And they're trying to help us out here. What we're trying to find is delta H plus over delta T, which looks like two different things, right? But together, it's the rate of change of the hydrogen ion. So what we want to do here is we want to say, well, that was the rate. What messes with us here is that this looks like one thing and that looks like one thing, and we're used to solving for one variable, right? But this isn't asking us to solve for one or the other. It wants the combination. And so what it wants is that whole thing. So we could say, well, that's like x, right? I'm solving for x. So this equals minus 1/2 times x. How do we find out what x is? Well, multiply both sides by 2 and negative 1. So we're going to get negative 2 times 0.00440. So negative 0.00880. And that's molarity per second. Any questions about that? So the hydrogen ion concentration is decreasing at a different rate than the iodide concentration is decreasing, right? But the overall rate of the reaction is the same, regardless of how we define it. And that says that I got the right answer. Let's see, is there a C? Okay. Predict the rate of change in concentration of H2O2 and I3 minus during this time interval. So again, they're saying change in concentration. The change in concentration is that big messy thing, delta H2O2 over delta T. So this is very similar to the previous question. We know what our rate is, 0.00440. And now we want to express it in terms of H2O2 instead of the other ones. So H2O2 is also a reactant, right? It's over here. So there's going to need it to be a negative sign. And then we multiply by 1 over the coefficient. Well, there's no coefficient. Well, we understand that it's a 1. So 1 over 1. You can write that if it makes you feel better, or you can leave it off. Doesn't matter. And then delta H2O2 divided by delta T. So remember, This whole thing is what we're trying to solve for. There will be questions like this on the first exam, and we're going to do some stuff that's more complicated than this. And then when you try to go back to do this, your mind's going to go, wait, what? And the tricky thing is, we're not looking for this value or that value. We're looking for the combination of them. So just watch out for that. So to find this, negative that equals this. This is actually pretty simple, right? Then this guy must equal negative 0.0044. So delta H2O2 over delta T, the rate of change of H2O2 is negative 0.00440 molarity per second. Everybody okay with that? So that's the first one. And then it's also asking about the I3 minus. Well, the rate of the reaction is the same. And let's write the expression for it in terms of I3 minus. This is a product, so no negative sign. And the coefficient is 1, right? 1 over the coefficient, just 1. So this is equal to the change in the I3 minus concentration divided by the change in time. And, we don't have to do anything. The rate of change for the I3 minus is the same as the rate of the reaction because its coefficient is 1. This one, the H2O had a coefficient of 1, but because it's a reactant and it's decreasing, it's negative of the rate. Any questions? Cool, I got the answers right. So your book also has what it calls conceptual connection problems. And these are ones that we should be able to do without a calculator. There might be a little bit of math we have to do in our heads, but not much. So it's do we understand the concept? So looking at this reaction, A plus 2B goes to C. Under specific set of conditions, we don't need to know what it is. The initial rate is 0.1 molarity per second. So it's asking what's the change in B over the change in T under the same conditions? Well, the 2 is going to come into this, right? And we need to be careful, because if we don't think about it carefully, we'll say, well, just multiply by 2. But that's not the case. So let's remind ourselves that the rate is equal to 4 for B, it's negative 1 over 2, the coefficient, times the change in B over the change in T. B changes at a slower rate because you need 2 of those for every one of the A's. So we actually divide by 2 instead of multiply by 2, and that's something that I would just write out the equation because I'd probably get it backwards on an exam myself. So just write it out. And so the rate is 0.1. So then what is this? This is our x that we're solving for, right? So we've got 0.1 is equal to negative 1/2 x. Do we divide 0.1 by 2? We multiply by 2. Okay, so the bad news is there's some algebra in this class. Okay, yes?
Multiply both sides by negative 1/2, and that's the same as divided by negative 2, isn't it?
If we multiply both sides by negative 1/2, then we'll end up with positive 1/4 x, right? So it can be confusing. So what I want to do is divide by negative 1/2. which is the same as multiplying by -2, right? So I'm going to end up with negative 0.2. Now, we didn't need a calculator, but it did get a little messy, right? And I misspoke earlier. B is actually changing faster than A. I had it backwards. Because for every A, we use up 2 B's, and so the B's are disappearing twice as fast as the A's are disappearing. These can be really confusing when you just try to think about them. I really like writing out the equation so I don't get things backwards. So our answer here is C. Questions? Is this something you just kind of have to wrestle through a little bit on your own? Well, how do we measure the reaction rate? You know, if we're measuring the rate of speed of a car, we can, say, okay, the car started here and it started there. Take a, tape measure or something, measure the distance, and we clocked the time and we divide. So we're going to do a similar thing, but we need to be able to measure the concentration of one of these things in order to determine the reaction rate. So there's 2 basic approaches. If this reaction is going to be done in an hour or so or less, then what we'll want to do is we'll continuously monitor the concentration of that thing. If we have something that happens over a very long time, maybe it's going to take 2 weeks, well, we don't need to sample continuously. We could maybe sample every 6 hours or something and see it changing. So I'm going to talk about these techniques. I'm not going to test you on them, but I just want you to have heard about them. So there are different techniques for continuously monitoring a species. And this can be the holdup in an experiment. How do we measure this thing, right? Because you pour these 2 things together, 2 clear liquids, and it's a clear liquid at the end, and you're like, how do I tell that anything's changing? How do I measure these things that are too small to see? So one way is called polarimetry. So if you have one of the components being optically active, meaning it rotates plane polarized light, then you can measure the change in the degree of rotation. So sugars are like this. There's a D and an L version, and one rotates light to the right and one rotates light to the left. And so in the solution, you can measure how much the light is rotated, and that's related to the concentration of the thing. This is a very old technique. Another way we could do it is by looking at the total pressure. So the total pressure of a gas is related to the partial pressures of all of these gases, right? So the total pressure would be the pressure of this plus the pressure of that and the pressure of that. And so as this reaction progresses, we're going to have more gas produced. The pressure's going to go up. So we could look at how much it's gone up and we could figure out what the change was. Another technique is called spectroscopy. So a lot of substances will absorb light. And so this is especially helpful when you have a colored solution. So a colored solution, let's think about like Gatorade or something, right? So you got the red Gatorade, and if you take a little bit of the red Gatorade and pour it into a bunch of water, the color changes, right? It's not as intense because there's less of the color in that container. So spectroscopy is where we shine a light through the solution and we measure how much light comes through. So through the original Gatorade, not much light would come through because it's really red. through the diluted Gatorade, we'd have less light coming through. And the amount of light coming through is related to the concentration. And so we can measure that and find the concentration of one component over a given period of time. There's examples of methods. There's a whole branch of chemistry called analytical chemistry, which is what I did my graduate work in, where we're trying to figure out how to measure things. Any questions? So I often get ahead of myself, and here again, I got ahead of myself. So here's the illustration for the spectrometer. So you have a light source, and you filter out most of that, so you've got a beam of light. You put it through a prism so that you can spread out the different colors, and then you have another slit that just selects one of those colors. You pass that light through the sample, and you detect how much is coming through. We're actually going to do an experiment like this in class. So an example here would be the H2 plus I2 makes two highs. Iodine is violet in color, H2 and HI are colorless. So what we see as this reaction proceeds is that the purple color of this gaseous mixture gets less and less and less. So we're going to see more light passing through, and we can figure out the concentration that way. For something that's slower, we'll do periodic sampling. We'll just take samples at different times. So this usually involves taking aliquots. So aliquot is this fancy science word for a sample from a solution. An aliquot is just a little bit of the solution that you pull out. So you take a sample out at particular times, and then you analyze the sample to figure out what's in it. This only works for relatively slow reactions, because if it's a fast reaction, all the stuff is in that aliquot. The reaction keeps going in the aliquot, right? So if you take the aliquot out and it's 30 seconds until you can get the result, well, the concentrations have changed significantly. If this is a slow reaction, though, they haven't changed much because it's going to take 2 weeks for the whole thing to go, right? So we take an aliquot out, and then we analyze that sample. And some common techniques are titration. You should remember that from Chem 1A. Hopefully no one has, really stressful memories about that. Gravimetric analysis. An example of this is you could add something to precipitate out one of those compounds, filter it out, and weigh it to see how much is in there. And that's one way to get the concentration. Or we could use something like gas chromatography. Gas chromatography can be used to measure concentrations of several different things in the mixture. So this is an illustration of how that works. You've got a carrier gas. This is usually something like nitrogen or helium, very unreactive. And so you've got this gas, and it's going through this skinny little tube called a column. And it comes out here, there's a detector. And so when it's just this carrier gas coming through, you've got basically no signal, just a flat line. We take our aliquot and we inject it into this stream of carrier gas, and it goes through the column. The column has a coating on the inside. They function in different ways, but different things in the mixture are attracted differently to the coating. Some things might, I like this coating, and I'm going to stay and interact with this coating, while the other things are going straight through. So things that don't interact with the coating very much are going to come through faster. You'll see here we've got a peak that's showing us that one component has come through, and then a little bit later, another component comes through. So we can separate them based on how they like the column. Okay? Any questions? Yeah, I'm not going to test you on these, but I just want you to have heard about them, right? And if you're interested in stuff like this, we have a chemistry certificate program where you can take a class and learn how to use instruments like this. We, in the new science building, it's so nice because we have this big instrument room now instead of everything crushed together. There's a huge room back there, and part of it is our instrument room. And we have a gas chromatograph. And in that class, you get to actually use the gas chromatograph. And you get to use all the other instruments as well. So we can talk more about that later.